This is the second lecture for section 2.1 on uh, on describing location in a distribution. In this section, we're going to talk about transforming data and a special kind of idealization of data called a density curve. Let's talk about transforming data. Transforming data means that we have a data set and then we do some sort of manipulation to it. Um, for example, we could end up adding the same number to every single observation in the data set. So what happens when we add the same number to every observation? Well, it ends up that it has an effect on any measurement of center or location. Now, centers are means and medians. Locations are things like the first and third quartile scores, the maximums and the minimums, and any percentiles. But what's interesting is that if we add the same number to all the observations, it has no change in terms of the distribution of distributions measurements of spread. That is range, IQR, and standard deviation. Let's take a look at this idea in the context of a problem. So soon after the metric system was introduced in a classroom in Australia, the students were asked to guess the width of their classroom to the nearest meter. The actual width of the room was 13 meters. A student who guessed 8 meters was too low by 5 meters. And then a student who guessed 40 meters was too high by 27 meters. We can examine the distribution of the guesses and compare it to the errors. So for example, here's a student who guessed, it looks like, let's see, he guessed 8 meters. How big was the error? Well, the error was 8 minus 13, or negative 5. And there's the negative 5. This point was transformed and became that point. Each point in this dot plot is being transformed into a point in the other dot plot. Now let's take a look at the summary of all of these data points. So first of all, there's the same number of data points in both distributions. Now, we're going to take a look at things like the mean. Well, geez, if I take the mean and I subtract 13, I get 3.02. Oh, the mean was transformed by that same manipulation, subtracting 13. So was the min, so was Q3, median, Q1, median, Q3, and the max. Each one of these numbers, you subtract 13 and you get the other number. And again, these are all measurements of location or center. Okay? But take a look what happened to the standard deviation. It's the same. The IQR is the same. The range is, in fact, every measurement of spread stayed the same. So again, adding or subtracting the same number to every observation has an effect on measurements of center and location, but no effect on measurements of spread. And you might also notice that the shapes are exactly the same. Okay, going on to the next page. The other kind of transformation we may have is multiplying each observation by a particular constant. What we see here is that if you multiply or divide measurements of um, each measurement, it has an effect on the center and location, but it also has an effect on the spread. Not by the same number b that you're multiplying on, but rather the absolute value of b. This being because if b happens to be negative, you can't have a negative standard deviation or range or IQR, so we have to make sure that we don't fall into that trap. But like in the other thing, it doesn't change the shape of the distribution. Let's take a look at an example how that plays out with this Australian student group. Um, One thing that we could do to their errors were in meters. And again, here's that kid whose error was -5, all right? But let's say we're trying to make it more meaningful to them, and they're still in a situation where they're still thinking in feet. Well, why don't we convert their error into feet? Now, to convert meters into feet, you multiply meters by 3.28. So if there's a kid whose error is 5 meters, then you multiply by 3.28 feet per meter. The meters cancel, and we end up getting uh, -16.4. All right. So again, in the transformation of data, each point in one data set, when it transforms into an exact to another point in the other data set. That -5 translates into that -16.4. So here's that -5. This is 0, -5, -10, -15, and you can see there that data point, which is then at that -16.4. By the way, it's in feet. All right. And what do we see when we look at those summaries? Imagine, if you would, I take 3.02 and I multiply it by 3.28. Do you think I get 9.91? I most certainly do. And this is true for every single number. Every single number in the original data set, we multiply by 3.28, ends up getting the number in the error data set that's in feet. All measurements are affected by multiplications. On to the next page. So we're going to shift gears a little bit. And in this next page, we're going to start talking about density curves. Density curves fall into this really big idea of like, what are we doing in general when we're dealing with quantitative data? Well, the author of our textbook suggests that there's really four things that we need to do. One, when we're talking about a distribution of data, we really need to always plot the graph. And that plot could be a dot plot, it could be a stem plot, it could be a box plot, it could be a histogram. But we get a real sense of the data by looking at the graph of that data, because that data will allow us to look at the overall pattern, the shape, and allow us to see striking departures from that pattern, the outliers. Now, we should also try to say, what do we think is going on with the center and spread? But we can do that as part of a numerical summary. Remember, the five-number summary included things like the median and the Q1 and the Q3, which gives us an idea of spread. All right. But not most of all, maybe if their overall pattern of observations is very regular, maybe we could describe it by a smooth curve. And that smooth curve is called a density curve. Now, by definition, a density curve is a curve that first and foremost is always on or above the horizontal axis. You can think of the density curve as kind of matching up with the bars of a histogram. And since our histogram bars are never negative, they only represent the presence of something, the density curve is going to also be either zero, no data, or above the axis representing some data. Now, the density curve is designed so the area is exactly 1 underneath it. And 1 is representative of the 100% of the data, which is represented by that curve. The last attribute, the density curve describes the overall pattern, the area under the curve, but above any interval of values is proportional to the number of observations that fall in that interval. Let me see if I can make that idea make sense. Let's talk about these scores. These are the scores from the Iowa Test of Basic Skills. They look pretty regular, so someone tried to fit a density curve on them. Let's say we're interested in what proportion of the students scored between 8 and 10. Well, that is a range on the horizontal axis that goes from 8 to 10. All right? If we go from that interval and we go up to the density curve and we find out what proportion, what proportion of that 100% is under that curve, then we know the proportion of students that scored between 8 and 10. This area is the proportion of students who scored between 8 and 10. All right. Now you're just like, how am I going to find that area? Don't worry about that for right now. We will deal with that in section 2.2, at least in terms of a special kind of distribution called the normal distribution. All right. Now, when we're describing density curves, um, we use the same kinds of expressions that we try to describe any distribution. We want to know shapes, we want to know center, and we want to know spread. So some of these density curves are symmetric, and some of them are skew. This one happens to be skew right. Now, it just so happens when the distribution is symmetric, the mean and the median are going to be right dead center in that distribution. And remember, median represents the middle point. That means the area under this curve below and up to the median represents 50% of the data. Now, if we have a distribution that's skew, it doesn't change the definition of mean and median, but it does change how they end up appearing in our distribution. The median still represents the 50% line. 50% of the data is in that line. But we know that the mean reacts strongly to the presence of outliers and skewness. That the data points here pull the mean further into the curve. Now, there's a physical representation that is talked about, and that is the mean ends up being the balance point. If you can imagine that this distribution was made out of a piece of solid wood, I could put that little fulcrum there. I could put that, and that shape would balance perfectly, right? But again, remember, mean gets pulled further towards the tail. Let's finish this off by looking at a check for understanding. Let's take a look at this diagram. And they said, why is that a legitimate density curve? Well, does it have the two attributes that density curves have? Is the curve at or above the horizontal axis? And the answer for this question is, yep, it meets that criteria. Is the area under the curve equal to 1, meaning it's equal to 100% of the data. And it says, yep, the total area under the curve is 1, so we meet the two criteria for the density curve. It says, well, what proportion of the observations lie between 7 and 8? Well, here's 7 and 8. Here's the interval in between them. And I go up to the curve, and I say, well, that area between the interval and under the curve is 0.12. So 0.12 or 12% of the observations lie between 7 and 8. So now, mark the approximate location of the mean. Okay, well, this point here called the mode, the highest point, okay, the mean will have to be to the left of it because of the skew left distribution. So I'm going to put the median, I don't know, about here. There's my guess for median. And again, there's my guess that this part is 50% of the data and the other part is the other 50%. Now, but what about the mean? The mean is pulled further towards the tail. So the mean somewhere to the left of the median. I'll place it about there. Okay? Again, not the 50% point, but further pulled um, toward the tail. And again, the idea being because the distribution is skew, in this case left, the median is left of the high spot, which we call the mode, and the mean is left of the median. All right. And that's it for section 2.1.